Welcome back. This is Dr. Desai, and I'm going to talk to you about self-assembly of straws in water today. So if you take a closer look, we have these straws attracted to each other using capillary forces, which I'll talk to you about later, and it's all spontaneous. So what actually happens is that some of these straws attract each other end to end, and some of them attract each other side to side, like that. So those are two different ways that they attract each other. So these straws are hydrophobic, which means that they fear water, which means that they are repelled from water in proper terms. Now, in this diagram, we see that there are, when we put the two straws, they're separated from each other, and you have the curvatures of the water actually being repelled from the straws, so they are further down than they actually are supposed to be. So this one curvature represents sort of an energy state, because the more, if you have a water that's of a water surface that's completely leveled, then you're not going to have as high of an energy if it's as opposed to if the water curvature is higher. So if in this case we have four curvatures, 1, 2, 3, 4, whereas when they're bonded to each other, because they're hydrophobic, they stay bonded, and they're bonded using the attractive forces of cohesion and adhesion. There are only two curvatures, which means that it goes from a higher energy state to a lower energy state, which means that there is a negative change in energy, or enthalpy, which I'll talk to you about later, and which means that it's exothermic reaction. Also, the straws, they go from a less ordered to a more ordered state. This is because so there are a lot of microstates. I can put these straws in many different combinations when they're all separated from each other, right? But however, when they come together, like they are over here, there are so few combinations that it's becoming more ordered. Now, because there are less possibilities, it's the entropy is decreasing. The entropy is basically the measure of chaos in the system. So now that we know the theoretical side of it, let's look at the mathematical side of it. We have the Gibbs free energy equation. Delta G equals delta H minus delta T delta S. Delta G is the Gibbs free energy. Delta H is the enthalpy, which in this case is negative, which means that it's exothermic. T is the temperature in Kelvin, and we're going to use kinetic energy to represent this temperature for this example. And delta S is supposed to represent the entropy, which is also negative because it's becoming more ordered. So if you have a negative and a positive T, because most likely the Kelvin is going to be positive, and delta S is negative, so negative times the negative makes it a positive, so you're adding to the delta H, which we concluded to be negative, so it would be a negative plus a positive, and this means that this is going to be spontaneous as long as we're talking about low temperatures. And spontaneous basically means that delta G is negative. If delta G is negative, then the reaction is spontaneous. So now, moving on. So as we've mentioned before, I'm going to talk to you about two ways that this reaction will not be spontaneous, or it will not work. So if I add kinetic energy, which is supposed to represent a higher temperature, that means that it's not going to be spontaneous because delta G is going to be positive. So I'm going to just agitate the solution so it will represent a higher kinetic energy or a higher temperature. So if we take a closer look, I'm going to just shake everything up. And see, as we see, they're all split up. And if I do this for longer, they're going to all be split up. So basically, if I add more kinetic energy, they're going to all break apart, and there's no way that cohesion and adhesion will let them bond together. Another way is if I lessen the surface tension, and this can be done by adding soap to the water. And I'm going to add soap, and it'll then break up the straws. I think that should be enough soap. And I'm just going to use the toothpick to break them up. And they're all, none of them are attracting to each other. And that proves those two theories. That's it. I conclude that if the conditions are proper, which means that there's a low temperature, or if the surface tension is completely balanced, so I have not added soap to it, the straws are going to self-assemble spontaneously. And basically, these straws self-assemble because of capillary forces, and because they are hydrophobic, they stay bonded and they don't just spread apart after being bonded, after being attracted. And that's it for today, folks. Look at my other videos on my YouTube channel. Thank you.